Hello everyone, welcome to AI Anytime channel. In this video, we are going to look at the first video of the evaluation series. So in the previous video, you would have seen that we mentioned that what are the topics we're gonna cover in this video series named evaluation of LLMs and RAG. So here we're going to look at the first method that will help us find out biases, the bias in the responses or the LLM workflow. Okay, so if you haven't watched the previous video, I will recommend you to watch the video. The link will be given in the description of this video, okay, where we have covered the introduction part of this playlist. That how are we going to evaluate LLMs and RAG approaches, okay, through different methods and algorithms. Now here I'm just going to open this in my Anaconda tool. I'm going to open Anaconda prompt cd and just Jupyter notebook. So we're going to write our code in a notebook. We'll take some examples, very intuitive, and we'll see what we're gonna do. So in this video, we're gonna look at WEAT, WEAT, Word Embeddings Association Test. Okay, that's what we're gonna look into this. I'll just do a note now. Uh, excuse me. I'm gonna open this in a new Python 3 notebook and let's just name it as evaluation of LLMs for biases using weight. And we're going to also look at demographic diversity analysis, which is very important as well. They mainly from a racism standpoint. Now here what we're going to do is, so we need few things here. Let me just add a markdown, and this detailed notebook will be given on my GitHub repository. Let's write v8, and in v8 what do we look at is we need so it's based on word embeddings. So here we're gonna just create a set of dummies embeddings, okay, but you can get it this word embedding through what to wake or glove or or any other embeddings model. This is what we're gonna look at here, right? And the other kind, so here we're gonna use cosine similarity, etc., and all of those things we'll use here, and we'll take some examples, and I'll show you that example, that how are we going to basically use that. Now let me just hit enter. Now let me first define sets. Here we have to define a sets of that's called a predefined sets. Once I define the set, you will understand that how are we going to evaluate this. Let me just write here something called define our sets. Now imagine if you have four sets, and the first two sets are X and Y, and in X you have a doctor. Okay, these are professions. Okay, so doctor, then you have engineer, and then you have, for example, let's have scientist. Now this X set is a set of professions, a job profile or a profession, and the Y is, for example, let's have the other set where we have nurse and teacher and then receptionist, and now we'll see that why I'm writing this, right? Because if you look at traditionally our society, the society that we have, if you find out the receptionist, still people say that I need a female receptionist, because the way that, and there's nothing wrong into it, by the way, the way they welcome people, the way they greet people, I think they are better than, I'll not say they are better, that might not be the right word, but they are as equivalent, okay. And so in traditionally it has happened that, okay, you need a female receptionist, you need a female nurse in a hospital, but it doesn't necessarily mean that the other gender cannot do that work. But this is how we define here, just as an hypothetical situation. Let's consider that, okay, we have two sets, we have X and Y. X is completely like a main gender, where you have doctor, engineer, scientist, and then you have nurse, teacher, receptionist. But I'm not saying that, by the way, but this is how society has seen, but now the evaluation has like it's evolving like anything, and you will see more diversity candidates over there. Now X and Y, and then what I'm going to do is, let's have an A here, and this A is nothing but it's going to be the attributes for gender. So it's uh, just like an entity that I'm defining. Okay, so let's do a man and then let's do a male, and then let's do a boy, and then the B is a woman, and then female, and then girl. Okay, so now you can find out over two sets of profession and two sets of gender, like the attributes A and B. Now these are our sets. Now for that particularly, we also need, for example, let's have some word embeddings. So how many we have? 3, 3, 6, 3, 9, 3, 12. So we have 12 different words. Now imagine if these are words, because we are looking at WEAT, Word Embeddings Association Test. So we need word embeddings for this, all of these associates. Let's see these as associates. Now, so for that I already have created word embeddings, dummy word embeddings, but you can get this word embeddings through an embedding model. So you can pass these words or the set of words through an embedding model like sentence transformer, any small embeddings model like tiny BZE, etc., etc. Okay, now you can get that, but for now, just to save some time, I have created a gist. Okay, let me just go to who your gist, and in my gist I'm gonna go inside this v8.py, and you can see the word embeddings that I've created. So let me just copy it out and come back in my notebook, and here I'm just going to define my word embeddings. Okay, now these are the word embeddings. It's, you can find out the word embeddings that we have, and this word embeddings, X and Y are the target words that we have in our example in the target word sets, and they represent different occupation that we know, and A and B are the attitude word set, okay, representing gender terms in the cases. Now we're gonna write a couple of functions, cosine, similarity, etc., etc., but let's see that here. Now to calculate the different associations between, first let me just run this word embeddings. Now we're gonna, what does happen? Name npy is, okay. We, let me just add import numpy as np here. Import numpy as np. And now this is going to be fine. So now for each word in set A, if you look at the set A that we have, right, we compute its differential association with both X and Y and then sum these values. So we're going to use cosine similarity. So similarly, we compute the sum of different associations for each word in set B as well. So for A and B, we will just compute the association with set X and set Y. That's what we're gonna do here. And the weight score is the difference between the two sets. That's going to give you a scalar value. Okay, that's what we're gonna do. So we're gonna take a average of cosine similarity to get a scalar value, not a matrix. So I'll explain that when I'm writing that part of the code. A positive weight score indicates that on average, words in set A are more strongly associated with words in X than words in B. It means that a bias towards it. And negative score indicates a stronger association between B and score. So if it's more positive or more negative, it means that it's biased towards this set of profiles. Now uh, let's understand that how we're gonna do. So now I'm gonna first define from sklearn dot uh, metrics dot pairwise. So let's excuse me, I'm going to use cosine similarity here. So import cosine underscore similarity. Okay, and now we're going to write a function. So define set of which is s, and they're going to pass three things: w, which will have some weights x and y, and then I'm just going to find out the similarity of x first. So let me just write sim x, and here np dot mean. So we're going to take the mean value of the cosine similarity. So let me just do cosine similarity of the word embeddings, and then giving w for each word. Okay, if for each words, w is each word that we're going to consider word embeddings, and let's reshape into, because we are using numpy here, so reshape of 1 comma minus 1, and then word embeddings of x, correct. Now with the words in A and B, that word that we have defined, all the words, then are 12 words over here. You can find it out over here, right? Now let's first look at into X, the association with X. So reshape, again 1 comma minus 1, and then for X in X. Now this is my sim X. I'll just copy it for similarity Y as well because it's going to be look very similar. We're gonna just change for Y there. Okay, now this W and all those looks good. Here X will become Y, and then here Y in Y. Okay. It says generator expression must be parenthesized. Okay. Okay. You cannot run like this. Now sim X. Now let me just do return sim X minus sim Y. And this is not sim X. I forgot to change that. Sim Y. Okay, so what we are doing np.min. We are looking at the cosine similarity. We're looking at the word embedding w dot reshape 1 comma minus word one embeddings x dot reshape for x in x for y in y, and just returning sim x minus sim y, and we have sw x wxy. Hmm. It says in generator expression must be parenthesized. Cosine similarity. This is correct. Word embeddings. Mhm. Cosine similarity. Word embeddings. W reshape. Word embeddings x. Word embeddings y. V dot reshapes. Something we are missing. This should be word embeddings. This closing is wrong. The parenthesized. Okay, I got that. Now this has to be here to end the parenthesis. Correct. Okay, now we have written sim x and sim y. Now this is a function that we have created. Now we will use this function to calculate the weight score for the word associations that we're gonna do. So let's call it weight score. And in this weight score, I'm gonna take a sum of uh, the sum of s, the function that we have. So sum of s and axy. So let's just do axy for a in a, and then I'm gonna minus this with sum of s, sum of s bxy. For b in b. And now let's print the weight score, and you can find out the weight score here. We get around 25% of 25, 0.25. If you get it in percentage, it will become 25, but it's a positive value. Okay, that we get it from here. Now how do we interpret from that particular value, guys? Now in a very simpler terms, if you look at this, right, uh, it appears to be a gender bias, a moderate bias, because the male terms are more closely associated with professions like doctor, engineer, or the scientist, while the female terms are more closely associated with the nurse, teacher, and receptionist. Maybe the embeddings is something that you can tweak around and have a look at how it's working. But this score is positive, indicate a bit of bias, a very moderate bias on this. So this is how you can use weight score to look at based on embeddings level, embeddings method that find out biases in your approaches that you are building. Now you will have word embeddings when you're working with RAG approaches. You will have different embeddings because you're working with a vector database. How can you look at these scenarios? At least from a validation standpoint, to find out if the weight score is more positive or a more negative, or how that is looks like. Now let's move to demographic diversity analysis. I'll just add some cells here, and I'm just gonna make it markdown and diversity. Let's write demographic diversity analysis. Now the objective here is to measure the performances of LLMs across different demographic groups. Now you have Spanish, you are in, if you are in French, German, etc., etc., right? Because there's the importance of demographic parity in LLMs, and that's what we're going to do. So we're going to measure model performance for each group. We'll define a couple of groups, and let me first bring it again. We're going to use sklearn here again. So sklearn dot metrics, and I'm going to import uh, accuracy score. So let's get an accuracy score. Let's imagine we have an LLM that has been trained to answer questions. Now we will assess its performance across two hypothetical demographic group, one being the native English speakers and the other being the non-native English speakers. So people who are non-native when it comes to speaking English. Okay, in their native places don't speak English, and in other group we'll have people who only speak English. Okay, now let's get the gist. I'll show you what we need here is just to save some time. I already created a set of question answer, and I'll explain that. Let me just copy it, come back here in notebook, paste it. Now imagine these are our questions. So we have questions: what is the capital of France? The real answer like Paris. Which gas do plants take in during photosynthesis, which is carbon dioxide? Blah blah blah. Who wrote Romeo and Juliet? So William Shakespeare. In which year did World War II end? And all of those are questions. Then we have native responses. These are all hypothetical responses that I have created just to test this out, because we are building a framework here, guys. Remember that these are the ways of building a framework where you can do a validation checks. Okay, now this will get changes depending on which LLM you are using. How how the scope looks like for your use case or a model that you have used, right? Now these are all hypothetical responses, but you have to replace this with the responses that you are getting from large language model on set of different questions. So if you look at the native responses, what are the capital of France? And so let's say Paris, and all these are native and these are non-native. And you can find out something wrong there. For example, which gas do plants take in during photosynthesis? It has oxygen, for example. It has 9044, for example, and it has only Shakespeare, for example, or whatever. Okay, now so let's create a function that will help us evaluate. So define evaluate. So define evaluate responses, and in this evaluate responses, I'm gonna use correct two parameters, correct answers and responses. And in this, I'm gonna have a correct count. So let's have a correct count, and this one I'm gonna sum this. So sum and one for Q A in correct answers dot items. We're gonna just get the items of it. If excuse me, if responses q responses q equals, it should be, let's call it a, because we have a in for qa, and then let's close that. Okay, this is the correct count. Now let's have an accuracy variable that will have the accuracy value, and accuracy that is going to be correct count, not correct answer, correct count defined divided by length of correct answers. Length of correct answers, this is your going to be. And now let's just return the accuracy. Okay, so this function will help us, right, evaluate it for both the native and the non-native. Now these responses you have to, as I'm again saying, these responses are again hypothetical. You have to get this from the LLM on your questions, and then you can use a similar function to find out the demographic diversity analysis. Okay, and the questions would be based on demographics, okay, where we have few groups or people who speak different languages in different demographies. Now here I'm going to just do a native accuracy. So native accuracy is going to be evaluate responses, and in this evaluate responses I'm going to have questions, and then I'm going to have native accuracy, not native accuracy, native how have we defined native responses? Native responses, and for non-native let's call it non-native accuracy, and this is going to be evaluate responses, and that's going to be questions and non-native responses. It says questions is not defined. Oh, I didn't run this or what? Oh, this is really surprising. Okay, I didn't run that cell. Okay, questions now. Let's print. So print and accuracy for native English speakers. Native English speakers, and then here I'm gonna just write a native accuracy dot to f. Okay, and let's just copy this thingy here, and let's call it non-native accuracy. And you can find out the value here for on the set of questions that we created, the hypothetical set of questions: accuracy for native English speakers and accuracy for native English speakers. Now you can find out here, this means the LLM correctly answered 60% of the questions posed by native English speakers and 20%, only 20% for non-native English speaker, but the samples are very less, right? If you can find out the sampling here, it's very few questions, 5 questions that you are, but if you increase it, it might the number might fluctuate, and I'm sure that it will fluctuate, right? Now there's a significant disparity. If you look at the how are we going to interpret these results, there are significant disparity in models performances between both the groups. Okay, the models seem to perform better for native English speakers, and that's how it is, right? For non-native English speakers, you will not get that much of accuracy when it comes to LLM responses. Now, it suggests that there is a bit of bias in favor of native English speaker or not adept at understanding the answers or the potential grammatical inaccuracies, because we have hidden something here, like for example Shakespeare, whatever, oxygen, wrong responses, etc., etc., posed by the non-native speaker, because this is our ground truth here, guys. These questions are the ground truth, and then we have responses for native and non-native. Now imagine if LLM has responded this and this. Okay, LLMs for this question. So, so this is what it is, guys. This is what I wanted to cover, right? In this video, the code will be available on the GitHub repository. You can go and find it out, try it out, and let me know if you have any thoughts, feedback. If you like the video, please hit the like icon. If you subscribe the channel, that's really great. Thank you for supporting. But if you haven't subscribed the channel, please do subscribe the channel. And that's all for this video, guys. Thank you so much for watching. See you in the next one.